What we've got here is a very sophisticated experiment. It's a modern piece of apparatus known as a tray filled with water. Now, I will do this bit here, which is to spread some powder on the top of the water. This powder isn't the essential part of the experiment, except to help the cameras see what's going on. In this jar here, Bryson has got some oil. Now, let me tell you what he's going to do, first of all, so that you can follow the thing. He's very gently going to release a microscopically small piece of oil, an oil drop, whose size we know exactly because this has been designed very carefully. Once the oil drops at full size, we'll drop it ever so carefully onto the surface of the water. And you see what happens. It spreads out, it keeps spreading, and it's stopped. Now, what's happened? Why has it stopped? It stopped because the molecules that were originally all combined together in that volume of that drop have run all over each other until there's just one molecule thick, and they've spread out into 2 dimensions. And at that point, they can't go any further. They're trying to pull each other apart, and that's as far as they'll go. It's like my piece of paper. They won't go any further. They've come to the natural extent. So you can see here the area that they've filled out, and you know the volume of the drop that you first started with. So comparing that volume, that 3-dimensional number, with the area at the end, which is a 2-dimensional thing, you've got 1 dimension missing. The area into the volume gives you the height of the molecules. This is spread out. If I know the volume of the starting thing here, which I do, and the area which we saw, I can do the calculation, and it's about 100,000th of a millimetre or thereabouts. So now you know the size of a molecule. Now, knowing that, we're on our way. We know the target that we're trying to get at. We know what we're going to have to do to see those things. What might also be interesting is to work out how many molecules make one of us. We know the volume of the molecule. All we need to do is to work out the volume of one of us. Now, can I have a volunteer who would like their volume measured? Right, maybe I should just tell you something first of all. How are you going to measure volumes? Now, one way of measuring volumes is this. If you have a big bath and you fill it up with water right to the rim so that one extra drop and it'll all go over. You then put something in it, in this case you, and all the water will splay over because you're going to get dunked right underneath this water. It's all going to spray all over the side. We'll collect it all up, see what the volume of the water is, and we'll know that's the same volume as you. Right. Who still wants to volunteer? Amazing. Well, don't panic. We're going to do it a different way. Would you like to come along? What Bryson has done here has created for us this incredibly sophisticated, novel, unique weighing machine. It's the most accurate weighing machine in this theatre. Now, what we're going to do, could you stand carefully on the 2 feet that are marked down here? Do it very gradually. Just put 1 foot on at a time. Okay, and now the other one. Right, and we see the liquid rising up. And you are just slightly less than 70 kilograms. Now, before you get off, can you swim? It's all right, don't panic. We're not going to do the water dunking. When you swim, I mean, if you didn't keep swimming, you'd sort of sink down. Your density is about the same as water. So from your weight here, if I pretend that you are made of water, I can work out the volume of water. 70 kilograms, 70 litres. That's how it goes. Every kilogram's a litre. So we've measured your volume. Thanks very much. Now, I'm going to do this myself because we had to work out the numbers, and let's see how I do. Right, I'm about 80. Now, from this, already beforehand, we worked out what that means in terms of the number of molecules that makes up me. We know the volume of a typical molecule. We now know my volume is slightly over 80 litres, and I have brought my calculators to the theatre to do the sum for us, and I think that the computer prints out the result somewhere over there. Can the computer print out now? It's approximately 27 times. 10 raised to the power 27. And you've got pretty well the same number of molecules. The number of zeros is the same for both of us. Probably you've got a 1 at the end and I've got a 3 at the end, but that's the only difference. So it's a huge number, and that shows you the size of that number. That's the number of molecules that make up you and me. Now what's interesting, thank you very much, we can lower it down now, so you at least each know what part of the human molecules you are. Now each of us is made of that number of molecules, and in turn those molecules are made of atoms. And inside each and every atom of you and me are electrons. And electrons are negatively charged carriers of electricity. So there's at least that number of electrons buried inside us. And later on, we're going to make use of that and get them out and do things with them. What we want to do first, though, is to see some of these molecules. What do we have to do to see these molecules? Why can't we just go and look at them with our eye? We know how big they are, and we also know the wavelength of light, how big that is. Let's see what wavelength has got to do with seeing things. Here we've got a beautiful graphic that's been drawn up, and it shows you the waves in the sea. The wavelength is the distance between one crest and the next. Now at the bottom of the picture, you've got a small boat. This boat much smaller than the length of the wave. Whereas at the top, you've got a very large boat, a boat whose size is as big as or maybe larger than the size of the wave. And you can see what happens here, that the small boat, that the waves just sweep by and are completely unaware that it's there. It doesn't reflect the waves at all. It's invisible. Whereas the large boat at the top, when the waves hit it, they reflect. It's just like the waves hitting me and reflecting into your eyes. You see me because the waves reflected. So this large boat will be seen by the wave, whereas the small boat will not. So you get the idea here that to see things, your wavelength must be smaller than the thing you're looking for. We can actually demonstrate that on a wave machine. What we've got here are waves being sent out across the whole of the surface, and this is analogous to light waves propagating through. The waves, when they hit things, when the light waves hit your eyes, you see things. Now let's see what happens when we put something in the way, like one of those boats. Put a large boat in, first of all. What you see is the waves coming in, hitting the boat, and being reflected. Behind the boat, there's a region of shadow where there's no waves at all. So the fact that the waves are reflected by the boat, somebody over here receiving these waves, if they were light waves, would see the boat. Somebody on the other side would see the shadow. So here, the large object can be seen by these waves. Now let's compare what happens with a small object.